Hello, good morning, good afternoon, or good evening, whatever time you're watching this educational video. At this moment, I will be introducing power in physics. Before we will, before we will proceed to some of the problems related to power, let's have the scenario first. Two weightlifters lifted the same 20 kilo barbell from a height of 2.1 meter. Weightlifter A did it in just 3 seconds, while weightlifter B did it in 5 seconds. The question are following: who did more work and who is more powerful? Okay, so remember, they carried the same mass of a barbell and then they also lifted it at the same height. That's 2.1. And then the question is who did more work? Remember that work is equal to the change in mechanical energy or change in potential energy or change in um, kinetic energy. In this case, since it involved height, so we will be dealing with potential energy. Work is equal to the change in potential energy. Potential energy initial is zero because it's on the ground. There's no height involved. But once it is lifted up, it generates or it measures a height now. So what we will be finding or calculating is the final potential energy. And the formula to get the potential energy, if you could still recall, it's just mass times gravity times the height. So if you will multiply 20 kilos and then 21 meters plus the height, the height 25 meters and the gravity 9.8. So both weightlifters A and B, um, they have the same the same amount of work done because they carry the same mass and gravity is constant and then the height is also the same. So they will have the same joules or both of them did the same amount of work. But who is more powerful between the two? Try to imagine that weightlifter A, he finished it or he lifted it in just 3 seconds while the other lifted it in 5 seconds. Okay, so try to guess. If you have a background on power in physics, probably you know the answer. I will spoil you now. Uh, uh, weightlifter A is more powerful than weightlifter B because or he just uh lifted it in a short period of time. The shorter the time and the greater the work, it's it's a powerful thing in physics. But in this case, we have the same work done. So the weightlifter who did it in a shorter period of time did more power. Okay. So in this scenario, weightlifter A is more powerful. Let's continue. All right. So before we will be dealing with the calculations later, we will define first power. Power is the rate at which work is done or energy is transferred over time. So it is our way to somehow describe how much energy is being transferred over a range of time. And we will use the symbol uppercase P for power. Mechanical power, it is most common is about how fast you're doing physical work like lifting, pushing, or pulling over a short time or over time. So that's mechanical power. And situations depicting high power magnitude or high power power or powerful situation in physics. The first one here, high or higher work magnitude in lesser time. You did more work in just a short period of time, then you have or the situation has a higher power magnitude. How fast work is done. Yeah. The faster the work done, the more powerful the situation. A car engine generates strong force, causing it to speed up. Yeah. If you're speeding so fast. So the time will become lesser and lesser, and the car engine generates more work. Okay, so how fast the work is done. Okay, so it's related to the previous high pen. Next is cyclist exerting more force on the pedal to speed up. Same with car engine generates. It's just that it's the cyclist exerting more force on the pedal just to speed up. Speeding up means lesser time involved and the work is greater in magnitude, so therefore it's powerful. Again, power is the rate at which work is done. And we all know that power is the rate of work done. And another way to say the amount of work expended over time, and the unit of power will be joules per second. That's work over time in seconds. Or it is called now watts. Okay? Hold on. All right. So we will agree that the W here means watt or watts. That's joule per second. You can definitely see this symbol um on the packaging of some device like bulbs, 50 watts. So meaning, uh, yeah, the amount of work done there and over a period of time. So that's why watt is used in some devices, okay, on the packaging or the unit they use. Okay, so we have here this table for me. It's helpful. Uh, For finding work done, we all know that work is equivalent to the change in mechanical energy, or we can also say it's equivalent to change in kinetic energy if we're focusing on kinetic only. And we can also use potential energy in that case. So work is equivalent to change in ME, mechanical energy, or work is equivalent to change in KE, or work is equivalent to change in PE, potential energy. Finding work done if work function with respect to time is given. So in that case, all you have to do is to substitute directly the specified time into the work function. Do not get its derivative, but just input or substitute the specified time on the function given. And finding power, it's the rate of work done. So we can have a mathematical expression of work over time. And remember, work is also equivalent to change in ME, so you can put it there. Instead of work, you can have it uh, delta PE or delta KE. And all in all, this will lead to this very wonderful and helpful equation of force times uh, speed or velocity. Okay, if we everything here can be derived um, in this equation here. Force multiplied by the speed, so you can also get the power. Especially if you cannot really, you cannot really find some other variables that will satisfy this equation or this equation or this equation or this equation. If in the problem you have the speed and you have a force, then probably it's a very helpful equation for you. Now, finding instantaneous power, the power in that particular instant moment. So it's the derivative of a work with respect to time, work function with respect to time. Okay. So in the following problems, we will be using which appropriate equations we can use. And don't also forget that force is equivalent to mass times the acceleration. If there's acceleration in the problem or the object is accelerating when applied, when work is being applied or yeah, force is being applied to the object, so probably sometimes acceleration is given. So don't forget also that weight is equals to mg, and then Fn also is equivalent to mg. And we can use some of the kinematic equations in solving for maybe acceleration or time or even displacement. Okay, problem A. So we have this picture. We have an angle of 27 degree, and if we will try to deal with this angle, first of all, let's try to know what are the vectors in this particular picture here. So in the problem, the mass of the skier is 60 kilogram being pulled by an engine. This is our engine motor, and it pulled the object all the way to this direction. Okay, and the mass of our skier is 60 kilogram. Okay, and it is being displaced. It's given here. The displacement is 45 meter. And then, of course, we have a normal force here. It's perpendicular to our surface, which is the slope here. And then it is not balanced by the weight force, but instead it's balanced by a component of a weight force here, which is mg cosine. Okay. And then its cosine. This is, I don't know, because it works for me so that I can recall what particular side will carry the cosine and sine theta, for example. If it's in adjacent side and the angle is is adjacent to the side, so definitely it will carry the cosine theta. And then always remember, like what I've always uh instruct during instruction or classes, this mg has component. So we have y component. This is the y component. And of course, this is the x component of, of the mg, weight force. And the y component here, I will try some other pen here. This y component is equal to this y component here. And if ever we will have another vector to connect here, it's equal to this vector. And the x component of the vector, I hope you could see it, it is equal also here. It, it carries the sine theta, okay? Um, because it's this side is the opposite angle. So it carries the sine theta if we will use the trigonometry trigonometry function here. This is equal. This is equal to this, and also this, and of course this. Mhm. So figure out the joules needed to pull the object up to 45 meter at an angle of 27 degrees. Then the speed is constant this time. When the speed is constant, velocity is constant, the acceleration is zero. And it's frictionless. No friction this time. So we will try to figure out the work done by the engine motor as it pulls the object all the way up here with constant velocity. Okay. And another thing, the power generated by the motor engine in pulling the skier. Okay. Let's try to find out the power, the rate of work. Okay. So let's have the continuation of our problem. Velocity is constant, so there's no acceleration. if velocity and speed is not changing, so the acceleration is zero as the skier is being pulled all the way up. And then the first thing we will be doing is to know what are the vectors along the x component or the x-axis. In this case, we only have one. Actually, we only have one, and this is the this one, mg sine theta. Remember that this component of the weight force is equal to this component of the weight force carrying the sine mg sine theta. So that's why we have the value of our vector along the x-axis. So we have mg sine theta. To determine the work done, work is equal to tension force. It involves tension force this time because the object is being pulled all the way to this um, slope upward. And then the tension force pulls the object via engine motor, and then we will multiply it by the displacement. And the displacement is very clear in the problem. It's 45 meters. Okay. So we can be able to substitute our mg sine, our I will change my highlighter here. It's mg sine theta to our tension here, acting along the x-axis, going up because it's being pulled by an engine motor. So we have it should be negative here. Okay, it uh negative. And then our displacement also is going to the left, so it will have a negative sign here. Our displacement should be negative, and negative, that's positive, so it will still have a positive work. Okay, no problem. Now, 60 is the mass of the object, 9.8 is our gravity, and sine 27, we got it from here. It's 27 degree, the angle of elevation of the ramp with respect to the horizontal, and we have 45 as our displacement. Again, it must be negative, and again, negative multiplied by negative, you will have a positive work because they have the vectors of the force and displacement um, are the same in terms of direction. So we will have a positive work here. It makes sense. So 12,012.59 joules, that's the work done. We're done with work done, but we need to find the power needed by the engine in pulling the object with distance or displacement of 45 meters. So if you noticed earlier, I showed a table that we have a lot of equations there to calculate power, but it will lead to this one equation here. Power is equal to force multiplied by velocity. Because in the problem, we have a constant velocities. It says 3 meter per second, so we will substitute it later here. The ft is still the same. We have the value of our component, x component of our mg. That's the value of your ft. So we have mg sine, and then we already got it a while ago. We will have it negative here, okay? And our velocity also, since it goes to the left, so we can put negative here. All right. It's just the direction, so no problem with that. When you will input all this stuff here, so we will have um, power is equal to 800.84 joules per second, or watts. 800.84 watts or joules per second. So this is the power needed by the engine in pulling the object. It does work approximately 12,059 joules. And you will just divide it by the time supposedly, but we don't have time in the problem, but we have velocity. We can be able to use it in order to get or to calculate or to figure out the power. Okay, I hope it makes sense. Now let's figure out power using conservation of energy. We have power is equal to, we will be using potential energy here because it involves height. If you notice on our diagram, we have height here. So we have to, it's good to utilize the change in physical potential energy. And potential energy is mgh. So we can get the height out from it. What's the height? And then we can also calculate the time if we want, right? Because we have a variable of time here. So let's use the trigonometry concept to evaluate the height. How to get the height, right? Since it wasn't provided in the problem there. So how are we going to get the height? So we will lead to this equation. Height is equal to sine theta times displacement. And I will teach you how did we arrived to that particular equation. All right. So as promised, I will show you how did we come up with the height is equal to the sine theta and displacement. In our diagram a while ago, we have this we have this angle here. It's 27 degree, and then this is the x component of our mg force or weight force. That's mg sine theta. It carries the sign because it's the adjacent side. Our height here obviously becomes our opposite. It's here. It's the opposite side. And our mg sine theta is the adjacent side. And our displacement is our hypotenuse. It's very clear. So the trigonometry function, in order for us to get the value of height, is SOA, right? That sine theta equals opposite, that's the height, and then divided by the displacement or hypotenuse. And if we will try to derive or isolate the height, that's why we have this formula here. Height is equal to sine theta times the displacement. Okay, so let's continue. Let's go back to the solutions we had a while ago. And that's why we arrive in this equation here. H is equal to sine theta times the displacement. And we will substitute it in our height variable here. So in that case, we change it. The height is being changed to the equation sine theta and displacement. Let's continue. We have all the values or the magnitudes of each of the variables here. So we can substitute it now. Okay. So if you will do it on your own, you will still arrive to our power equation a while ago, which is force equals velocity. So it's pretty sure that our answer is still the same if we will be using this formula to get the power using conservation of energy. So yeah, at the end of your solution, you will be directed to this equation. So the answer is still the same. Let's proceed with problem B. It involves elevator situation this time. If you could still recall the elevator situation, it depends upon if there is an acceleration or no acceleration. So a 575 kilogram elevator moves from rest. So velocity is 0 up to 4 seconds with a constant acceleration. So we have a constant acceleration this time in this scenario as it reaches its constant cruising speed at 2 meter per second. It's going to be our final velocity here. Okay. And from rest, so we have zero initial velocity. Uh-huh. So it involves elevator and its tension force is being involved here, plus the acceleration. Acceleration is present. And in an elevator, it moves upward, right? It moves upward. So we have our forces along the y-axis this time. We try to analyze what are the forces along the uh, y-axis. Of course, we have the tension force going up, and going down, we have the weight force or mg. Plus, we have an upward acceleration there. So these are our vectors later. And now figure out the average power of the elevator during this period. Just the average power. That's our task in this problem. Okay. All right. So we have the given variables in the problem. We have time here, 5 seconds. And then we have the mass of the elevator, 575. We have the velocity, final velocity, 2 meter per second, and we have the gravity there. It's understood that gravity is always there. Okay. Acceleration is not zero this time. There's a constant acceleration going on, and it's upward since the elevator is going up. Okay. So we will be determining what are the forces along the y uh, y-axis. Okay. And we have, of course, the tension force going up, so that's why it's positive, and we have the weight force going down. Again, going up, it's the Ft, then going down is mg. That's why it's negative here. And since it's not a zero acceleration scenario, so we can incorporate F as ma. That's, yeah, force is equal to ma because we have acceleration this time. And we will do something. We will isolate Ft, the tension force, because we will be using the tension force later in calculating the work done. So we have a simplified version. We have Ft and then mg plus ma. We transferred Ft here becomes negative, and we transferred the ma here becomes negative, and we multiply both side by negative sign, and the signs changes from negative, it becomes positive. The negative mg becomes positive, and then the negative ma becomes positive, and then the negative mg also becomes positive. Okay, so now let's calculate the acceleration. Okay, don't be confused. We just derive it to the point that the ft should not carry the negative sign. So we multiply both equations by a negative sign to make it positive. So the negative the negative ma becomes positive, and the negative mg becomes positive. So that's why we have this equation here. Okay. Calculate the acceleration. How to do it? By simply using the formula of acceleration. That's delta velocity over delta time. In our case, it started from rest, so it's 0 to 2, and then 0 to 5 seconds. You will have 2 over 5. You will have a quotient or an acceleration of 0.4 meter per second, or meter per second squared. Okay, let's substitute the acceleration value to our equation earlier. So we have Ft is equal to mg plus the ma. So we will substitute now the value of acceleration, 0.4. If you will input all this stuff on your calculator, it will give you a product of 5865 newtons. That's the force of the tension as uh, it goes up, right? And now let's figure out the work done. And if you notice, we have already the value of your FT, the tension force, but we do not know what is the displacement because it's not part of our problem. So we need to determine the displacement using our kinematics, and the perfect kinematic equation for that is this. Displacement is equal to initial velocity times time plus 0.5 times acceleration and time squared. Remember, velocity initial is 0, so we can somehow omit this term here. So we have 0.5, 0.4, t 0.4 is the value of our acceleration and 5 is the value of our time in the problem. So if you will multiply all this stuff correctly, you can have 5 meters as the displacement. And now we have the 5 meter in our calculations or solutions. We can uh, figure out work done now. We can substitute 5 as the value of our displacement in our force 5865 that we calculated a while ago. And we have work done that's equivalent to 29325 joules. And the last thing, we need to find the average power. How to do it? Yeah. Work, we calculated it recently from this solution, and we will just have to divide it by 5, and we will get a quotient of 5865 joules per second. That's the average power. All right, now that we have the value of our acceleration, hold on, I will change the color of my highlighter. We have the acceleration, we calculated it recently. We also have the 5 meter as the displacement. And this time, there's another way to get the average power if you're not using if you don't like the other way around. You can also use this one. We will be using the concept of conservation of energy. We all know that work is equal to the change in ME. So we can say that change in KE plus change in PE. We will be using that equation and finding the work done. And remember the formula to get your KE at 0.5 mv squared. This is really the formula of kinetic energy. The formula of potential energy, we have mgh. Okay. So in that case, we will plug in these equations to our um, formula here. So work is equal to 0.5 meter per second squared plus mgh. Figure out the work done. We will substitute all the available units there. So for work, we have the mass is 575. We have velocity 2. Then we have mass 575. We have gravity, and we have the height. The height is going up, so it's like 5. That's the displacement. And then we have this two factors here, products, and we will get the sum of these products. We have to 9325. And if you notice, we arrive at the amount of work we calculated recently. It's 29325 as well. We will divide it by we will divide by 5, and we will have this same value. Thank you. So we have problem C. It's a typical example provided uh, on books or problems in the book, in physics book. Okay. It says here a machine lifts a 100 kilogram object to a height of 10 meters in 5 seconds. Let's figure out the amount of power output of the machine. So if you notice, the given we have, it's understood gravity is there. Gravity is there. We have the mass, height, and time. Okay. And our formula to get the power output is just work over time, the rate over work, right? And since we do not have the value of work yet, so all you have to do is to figure out the joules first. And remember, in my previous slides, um, force is equal to mg, right? Mass, here's our mass multiplied by our gravity, 9.8. So that's how we can get the work or our joules there. So from that, since force is not provided, make use of the formula F is equal to mg. And in that case, 100, that's the mass times the gravity. So you will have 980 newtons, and we will plug in that value here in our F. So 980 times 10, 10 is our displacement. So we have 9,800 joules as our work done here. And the time is in 5 seconds. All you have to do is to um, yeah, put it here in our equation. We already have the work done. It's 9,800 joules divided by the time. So you will have 1960 joules per second or watts. Problem D. A crate accelerates across a frictionless force. The work done here is work with respect to time. By the cable's force on the crate is a function work with respect to time, and this is our function given here. We're in W, or the work is in joules and time is in seconds. The unit of power, that's joules per second. Okay, so we have a function here given. And in order for us to calculate this, the first task we have is what is the average power done by cable's force from 1 second to 7 seconds. We need to get the average power. And what is the instantaneous power, or the P-inst, done by the cable's force from 1 second? End, not two, but it's end. Because if it's two, we have a lot of uh, you know, processes to make, or steps to make. So it's not two, but it's end. Okay, and 7 seconds only. 7 seconds and 1 second. So we need to get the instantaneous power there. Okay, what is the average power? Let's have first the average power done by cable's force from 1 seconds to 7 seconds. So if you could still recall, when we want to find work, if work with respect to time function is given, you have to substitute directly the specified time into the equation or the function. So you have one, you have to directly substitute it to the function, and another task is to substitute 7 to our function. It's the formula. Let's figure out the work at 1 second and 7 seconds. Let's begin with 1 second using the function given in the problem. Substitute directly 1 second to the time variable, and then you will have 3.75 joules. And substitute 7 seconds in the time variable in our equation, and then you will have 57.75 joules. Now, to figure out the average, let's change in work over change in time. So all you have to do is to get the difference of your 57.75 joules. It's the work at 7 seconds. And then the work done in 1 second, that's 375. And you will get the difference. You will also do the same with the delta time. And from that, That's the amount of, or that's the average power from 1 second to 2 seconds. Now, another task, another problem to be solved is what is the instantaneous power done by the cables from one end? This is the correct one. 1 second and 7 seconds. In our table earlier, finding instantaneous power, we have to do the derivative of work with respect to time. Okay, that's our formula. Let's figure out the instantaneous power at 1 second and 7 seconds. Let's begin with 1 second. So we have the derivative of the function. If you could still recall how to do the derivative, yeah, all you have to do is to, since we have two exponent here, we will multiply it to 0.75. And then from 2, we will have it minus 1. So it will become T1. Okay. And then in this part, we have 1 here. It understood that this exponent has 1. So 1 times 3, and then 1 minus 1 is 0. So we can cancel x, and we will remain the constant, or the 3 coefficient here. All right. So we can have it this way. So 2 again, when we do the when we get the derivative, 2 multiplied by 0.5, and you will have 1.5. That's the product of 2 times 0.5. And then 2 minus 2, that's 1. So that is why we have 1 here at t. Now, the next term, we have x here. It understood that we have 1 exponent. So 1 times 3 is 3. And then 1 minus 1 is 0. So we cancel x there. Okay. Let's substitute 1 second to the derivative, because we finally calculated, or yeah, get the derivative of our work function with respect to time. And we have this instantaneous power at 1 second, 4.5 joules per second. At 7 seconds, still the same function. So we will arrive with this the first derivative, and then we will substitute 7 to the derivative, and then we have the answer. That's 13.5 joules. That's it. Thank you so much for watching. I hope this will help you in your review soon for your upcoming exam, and see you around. And yeah, if you like it, yeah, just subscribe. Thank you so much. See you around next time.